In this video, we are going to talk about velocity, speed, and acceleration. So everything is going to go back to some concepts we talked about in a previous video. So if we have a position equation, which would be, usually we use negative 1/2 g t squared plus v naught t plus s naught. We know that the velocity equation is the derivative of the position equation, and acceleration is the derivative of velocity, or the second derivative of the position equation. If we want to know speed, then speed is how fast something's going, but it's not giving us a direction, whereas velocity is going to give us a direction. And we could think about these things in terms of vectors, and you'll talk more about that if you take Calculus 3. But for us, speed is going to be the absolute value of the velocity. So everything goes back to this idea of average rate of change. Average rate of change is just a fancy way of saying slope. So if we're looking at a function, f of x, and I'm looking at a point x equals a here, and if I were to scoot over h units, then this point would be this plus h, so a plus h, and we know every x coordinate on this function would have a corresponding y coordinate. So this would be f of a. This y coordinate would be f of a plus h. So slope, if you remember, is y2 minus y1 over x2 minus x1. So if we think about these ordered pairs, this is a, f of a, and this is a plus h, f of a plus h. So it would be y2, f of a plus h, minus y1, f of a, over a plus h minus a, just using the slope equation, which is going to give us f of a plus h minus f of a all over h. So that's where this equation is coming from. And we know if we want instantaneous rate of change, so what's happening at a particular moment in time, then we could take the derivative. And that secant line would approach the tangent line would approach the secant line as h gets smaller and smaller and smaller, which is going to change our value of our slope. And we could show that by taking the limit as that distance between these 2 points shrinks, so it approaches 0. Now, if we have small enough values for h, so if our distance between these two values is super small, then we can use that derivative and say that the derivative will be approximately equal to the slope for the secant line. So to show this, let's say our h value, and I'm going to zoom in on my little picture here. Let's say my h value was really small. Now, would you agree that that slope here is pretty steep, we would say? But if my h was really small, maybe my second point was here, so my h was this value, then you can see this second point is really close to that first point, and that slope between these 2 points, and they are secant, this is a secant line, would be really close to the slope of the tangent line there, all because that h value is super small. And if the h value is small enough, then the slope of the tangent line is really going to be close to the slope of the secant line, which is what this statement is saying. So the secant line is about equal to the slope of the tangent line. Let me try to clean up my writing here. So then let's take our little equation and let's solve this guy for f of a plus h. So we can multiply both sides by h, and then we could add this f of a to the other side, and we could get an approximation for f of a plus h. So we could figure out what this would be our new x plus h, f of x plus h. We could figure out what that, let me fix this, a plus h here. F of a plus h, f of a plus h. There we go. So we could figure out what that y value would be based on what we know about the approximate slope between those 2 points. And that's what this is telling us. And this is used for things like marginal analysis. Maybe we're in a business setting and we want to know, we know the cost of producing X amount of items. Maybe we're producing some kind of game system. Then what would be the cost of producing one more game system? And then we can analyze, is it worth producing more, or do we need to stay where we're at, or maybe even do we need to produce less? So that idea is used a lot in business applications. But for now, let's go back to this idea of velocity and let's look at a few problems. A ball is dropped from a height of 64 feet. The height above the ground can be modeled using this equation. A is asking us what's the instantaneous velocity of the ball when it hits the ground. So to find the instantaneous velocity, we are going to find the derivative. So the derivative of this guy is negative 32t. We want to know the velocity when it hits the ground. Well, we've got to figure out what time does that happen. So the height when it hits the ground is going to be 0. So we're going to set 0 equal to negative 16t squared plus 64t. And then we'll know what we're going to plug in here. Oh, it's just 64. Let me fix that. So to solve this, I'm going to move that 16 over. Now I'm going to divide by 16. So 64 minus 16, divided by 16 is 4. And then t is going to be equal to plus or minus 2. And since we're talking about time, the negative t doesn't make sense, so we're going to use 2. So we know this is going to model the velocity. So we want to know the velocity at 2 seconds in. And that velocity is going to be negative 64, and this would be in feet per second, because we're telling us units up here. B is asking the average velocity during the fall. So to find the average velocity, this is not going to use the derivative. We are going to just find the average at 0 seconds, and then at 2 seconds when it hits the ground. So we need to figure out the height at 2 seconds and at 0 seconds. So if we plug 0 in here, we're going to get 64. And if we plug a 2 in here, we're going to get 0. So we're going to find that average rate of change between here and here, and that's going to be that slope of that secant line. So 64 minus 0 over 0 minus 2 would be negative 32 feet per second. Let's look at another example. Particle moves along a coordinate axis in a positive direction to the right. Its position at time t is given by s is equal to t cubed minus 4t plus 2. Find the velocity and acceleration at t equals 1 and use these values to answer the questions. So the velocity would be 3t squared minus 4. And if we were to plug a 1 in, we're going to get negative 1. Acceleration is the derivative of velocity. And if we plug in 1, we know the acceleration at time 1. So let's look at what's going on. Since our velocity is negative, at time equals 1, then that tells us the particle is moving from right to left. Now the acceleration being positive and the velocity being negative is telling us that these things are acting in opposite directions. So even though this is moving left to right, then our particle is speeding up in that direction. Let's look at the next one. So we have a position equation for a particle. If we want to find velocity, we're going to take the derivative. So we're going to get 3t squared minus 18t plus 24. We want to know at what time is the particle at rest. Well, that's going to be where that derivative is equal to 0. So I'm going to set the velocity equal to 0. At rest means it's not moving, has a velocity of 0. So I can divide all those terms by 3. Let me try that again. Divide by 3, divide by 3, divide by 3. So this is t minus 4 and t minus 2. So there's 2 times we're going to have a velocity of 0 at 2, and then again at 4. So he's asking on what time intervals is the particle moving from left to right and then right to left. So let's create a sign chart for this. So we've got 2 and we've got 4. And we're going to substitute numbers into the velocity equation, which is the derivative of the position equation. So let's plug in 0. If we plug in 0 into that derivative, we're going to have 3 times 0 squared, which is 0, minus 18 times 0, which is 0 plus 24. So we're going to have a positive. If we plug in something like 3, we're going to have 3 times 3 squared, minus 18 times 3, plus 24. So that's going to be a negative. And then if we plug in 5, we're going to have 3 times 5 squared minus 18 times 5 plus 24. So where the derivative is positive, The particle is going to be moving from left to right. And then where it's negative, it's going to move right to left. So let's create a little chart. We have some key times in here, and then we want to know position. So we're going to start at time equals 0, and then we're going to figure out what's happening at time equals 2 and time equals 4. We're going to create a little diagram here. So I'm plugging these numbers into my position equation up here. When I plug 0 in, I'm going to get 4. So at time 0, this position is at 4. When I plug in 2, and I'm going to do this off screen with my calculator. We're at 24, and at 4, we're at 20. So let's draw a little picture of what's going on. So I'm thinking about the height of this figure. Let me draw it vertically. So at time 0, this thing has a height of 4. And then 2 units over, it's going to have a height of 24. So this is 5, 10, 15, 20, 25. So you can see how this is increasing here. And then at 4, it has a height of 20. So this is how the particle is moving. It's coming up, and then it's going down. And then it's going to end up going up again. Going up, down, up. So we're moving like this. So if I think about this horizontally, which is how this textbook likes to do things. So here's a 0, and this is going to be distance. So we're at 4 units at time equals 0. And then at time equals 2, we're at 24 units. And then we're going to back off to 20 units at time equals 4. So we're kind of moving this way. We're stopped, then we move in this direction, and then we end up going back and then moving that way.